I'm not even sure whether it would be implementable, but let's say it was, and we could have a .size method to the type info object, then that would surely not be something known at compile time. So static assert wouldn't work, and that breaks our requirement from the beginning of the talk. So that's why I just inserted that stupid requirement, because I wanted to show that it's really important for us to retain the information which is known at compile time. We want to retain it so that when we manipulate it later on, we're able to manipulate it in a way that is known at compile time too. That's like that's the important part. All right. So what if we had a static type info kind of thing? So this static type info here, since we're passing the type as a template parameter, then it's possible in the body of the loop, it's possible to say, hey, you're a static type info, therefore you have a nested alias called type, and I know that is the actual t, so that I can do size of t, and it's going to give me the right answer. Are we not in good shape? I mean, that would kind of work. Is everybody following me here? I decal type my C, so that gives me a static type info thing, and then I get the T inside there by using column type. And once I have the T inside my loop, then I can use its size. Right? The only problem that we have is that static type info of A, static type info of B, and of C have different types. So we can't put them in a vector, because a vector may only hold objects that have the same type. But fortunately, now we have tuples. So we have a sequence which can hold objects of different types. So basically, we create a tuple containing our static type infos. Then, assuming that we have a construct that allows us to loop over a tuple, then we can definitely get the t and then the size of its t. Is everybody with me here? Right? Yes?
Could you just break down line 4? Maybe I'm just not familiar with this.
They're here?
Yeah, that one.
Okay, sorry, that's a type def.
Okay.
All right. So this is equivalent to saying type def, type name decal type C colon type space t semicolon. So essentially, forget about the type name. This is because C++ is this is not important. But essentially, what's important here is like I'm aliasing, I'm type defing. Okay, T to be decal type C colon type. And what is decal type C? Well, if you're at the first element in your loop, then C is the first element of the tuple, so that's a static type info of A, right? And when I fetch the colon type inside there, it's going to be T. So it's going to be A in this case. All right, you follow me?
Yeah.
So here, for the first element, for the first time around in the loop, T is equal to A. Replace that by A. So then you have type ID A.name, size of A is smaller or equal than, is less than or equal to 1,000. The second, the second time around in the loop, then T is equal to B, because the second element in the sequence is a static type info of B, and so on and so on. And the difference between this and well, this is that really the static type info knows the T inside it. It knows the type that it represents. It knows that at compile time, it carries that compile time information as a compile time information through an alias inside it. Whereas std type info, you cannot possibly ask like, hey, you are just a std type info. Tell me what type you represent at compile time. It doesn't know. It can tell you at runtime though, but it can't tell you at compile time. So the static type info knows that at compile time, But the drawback is that it cannot be held in a stud vector or any other data structure that expects objects to have a fixed layout, a fixed type, a fixed interface, so on and so forth. All right.
So you mentioned about assuming having a for loop over tuples.
Assuming having a for loop over tuples.
And it can be executed in compile time, not in run.
That for loop?
Yeah. The for loop has to execute in compile time.
So assuming we have a construct which allows us to take this code here and call it the first time around with C equivalent to stdget 0, and then C is equal to stdget 1, and so on and so forth, the tuple. You were first.
Related to that previous question, in this slide and the previous slide, why do you use using rather than top def?
Why do I use, the question is,
So
why am I using instead of type def? It's just a matter of style.
It's just what the cool C++ 14 and 17 people do.
It's just, yeah, what the cool C++ 14 and 17 people do. No, actually, it's more consistent for a simple reason. You can have template aliases. You can have template type name something, and then using whatever you want equals something. So it's a template type def essentially, but you can't do that with type def. So always using is more consistent because every time you want to alias a type, whether it is through a template alias or not, you can use the same construct, exactly the same construct. So I like that better. And the other thing is, I personally, once I got used to it, I personally think that this reflects much better the fact that we're assigning a type to another type, right? So it's a matter of preference, I guess. In that case, I could have used either. Yes?
Okay, so just at this slide in the void, why do we need the static type info? Why not just have a tuple of ABC and just, yeah.
Great question. Okay, so the question is, here, why can't we just have a tuple of A, B, and C? And you said,
Cannot put A, B, C.
well, did you say assuming a void?
Yeah, no, I just said in the void.
In the void.
I
Okay. Well, the reason is assume that A is void or something like that.
Okay, sure.
Okay. What if A is an incomplete type? What if A is something that is not default constructible? Boom. What if A is what if A is well, anything that doesn't work in a tuple, right? The tuple expects, because a tuple is basically just a struct.
I guess then my real question is, why are you using tuple instead of type list?
You'll see quite soon, because type lists means type level algorithms, which means Angley brackets, which means nightmares. Whereas this means, oh, I'm closer to manipulating actual objects, and I'm therefore closer to the normal C++ syntax, which I love. That's basically it. But yeah, this here is isomorphic to a type list. And I mean isomorphic in a strong sense. This is what I made my bachelor's thesis on. So like this is exactly the same thing as a type list. But the syntax will be different.
Okay.
This is the only reason. But so the reason for not using tuple of A, B, and C is because it doesn't work in the case of void, in the case of incomplete types, and cases like that. And I mean, in this very precise case, you might get the, well, no, you wouldn't even get the right thing. Function pointers, they decay.
Yeah.
That kind of stuff. Yeah, so you wouldn't get the right thing here. All right, so we only need to iterate in a tuple. All right, so 49 minutes in, and we can't do much. Fortunately, I spent like 3 years of my life doing this. So yeah, I wrote the bit that does the for each here. So I did it for you so that you don't have to worry about it. Essentially, what you have is a stud for each equivalent that's going to work on tuples. Right? Isn't that nice? And just like stud for each, well, you can use lambdas, right? Which makes for more expressiveness. For anybody that has already done metaprogramming before this syntax was introduced. Here, like, you have to use what they call the lambda expression, and it's not always super readable. And you can't possibly have stuff that's runtime inside the lambda too. I'm doing a bunch of stuff here. I'm extracting the t at compile time as a compile time information. I'm doing something at runtime, and then I'm doing something else at compile time, all in the same block. This is much closer to the normal usage of algorithms than what we would have to do if we had to separate, to basically box ourselves in the compile time only world, which was there before. But I'm assuming no prior knowledge of metaprogramming. So before this, it was really painful. Now it's at least reasonably. It's not too bad, I guess. At least it kind of looks like a stood for each. So it's not a range-based for loop, but it's not too bad. I saw that there was kind of yes.
Does this work now? I guess the polymorphic lambda, is it in 14 or is it, do we have to wait until 17?
That's 14.
14.
That one is 14. Yes. Oh, thank God. I would be a sad man.
It's even simpler than stood for each, right? Because you just have to give it the container and not begin and end.
What's that?
It's even simpler than stood for each. Your HANA.
Yeah. Okay. Right. Yes. He says the comment is it's even simpler than stood for each because I take a container and no beginning end. Yes. Correct. Yeah. So all the algorithms that I will show today, they take the container itself. They don't take iterators. ANA doesn't even have iterators. Iterators are a really nice abstraction for the runtime world. Then again, ranges might come and say like, hey, bye-bye iterators, but I mean they're well, not quite, but I mean they're a really nice abstraction for runtime, but for compile time, iterators don't really have their place. Yeah, previous libraries were based on iterators like MPL and Fusion, but it led to some design choices that were not necessarily always optimal, both in terms of compile time performance and runtime performance, but mostly about compile time. And usability, because frankly, this is slightly more terse than having to do that again. So anyway.
I have a question.
Yes.
I'm still confused by the using T
All right.
operation because I'm used to thinking of types as being known as at compile time, whereas here T
They are.
can be one of several types.
That's right. Well, it's auto here, so it's also known as compile time. So bear with me.
Okay.
This is equivalent. This is equivalent to this here, right? All right. So get 0 of classes, assuming that I have my std type info of A, B, and C. This here is equivalent to calling f with an argument that is a std type info of A. Therefore, the auto here, which, if you know lambdas, is equivalent to having a template operator parens inside the anonymous struct that is generated by the compiler. Basically, that means that C here is really a std type info of A. Therefore, its type is known as compile time. There is one f that is generated. There is one operator parent. Okay, there is one body here that's generated by the compiler on this line. There's a different body that is generated. There's like a different operator parens that is generated for this line here, and that operator parens, as inside its angle bracket, inside its template parameter, it's as static type info of B instead of static type info of A.
I think you have a slide somewhere where you have a range for loop, like for C classes, and then you have using T.
Yeah.
And
That was-
that's really confusing because then T will have a different type at each iteration of the loop.
Right, so the comment is that there's a slide somewhere where I have a range-based for loop, and I use C, but my loop variable is C, but then C as a different type each time over. Yeah, I know, that's just pseudocode. It's just to express what we would like to.
Here
Oh,
is a
got it.
typo, there is a capital C instead of a capital T everywhere.
Was that?
There is a capital C instead of a capital T everywhere. Yeah, it should be T.
Desired.
Yeah. that is indeed a typo. Thank you very much. That should be T here. Oh God, that is awful. I mean, yeah, it must be really confusing. I'm sorry. So that is T, 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 and T here. Okay, right. Is everybody with me? I mean, this is like the most confusing thing ever. I mean, I wrote the slides and I wrote the library, so I'm like, yeah, even with a typo, I'm fine. But like, yes.
So that's what you meant by polymorphic lambdas. You've got a lambda expression that's instantiated 3 times with 3 different types.
That's right.
Got it.
So this is a polymorphic lambda. It gets instantiated 3 times with 3 different types. And so 3 different bodies are generated by the compiler, and this is why inside each body we can know the type with which we were instantiated, and we know that well at compile time, obviously, because it's just an instantiation. So is everybody with me? Even with a typo?
Find out.
All right. So basically we create. Okay. So here's how we do. We create a static type info thing, static type info struct that's going to hold the type information for us at compile time. Then to manipulate that, so now since this is really like if you create an object of that static type info thing, it's just a normal object. So it's a first-class citizen of C++. We're good. We can store it. We can like return it from a function if we want. We can pass it as a parameter and that kind of stuff. But if we want to have multiple such static type infos inside a data structure in order to process it with algorithms, we can't because they have different types. So then we create our own data structure that can contain objects with different types, which is the tuple, and then we create our algorithms that can process these data structures, and then we're good. So that's what we did. Right? Now, HANA provides this static type info. It's just called HANA clone type. And you can use tuple or HANA tuple. So now, if everybody is with me, I will go on to heterogeneous data structures and algorithms. So I will dive deeper inside this thing. I will present more algorithms that are kind of like for each, but more complex, like sort, for example, and that kind of stuff. And I will also show a few data structures that are useful, because sure, a state vector is useful, but sometimes you need pseudo-normed map. And just the same, in metaprogramming, sometimes you need a tuple. You need something which is indexed by indices and sequential. But sometimes you might also want to key on something else, which is not necessarily an index. And then you need a compile time map. We'll get to that. So at this point, I would expect you to understand the basics of tuples. Like a tuple is essentially a struct, but that can also be seen if you put the right classes on. It can also be seen as a sequence that can hold objects with different types, so a heterogeneous sequence. And I would expect you to understand how tuples can be used as a basis for metaprogramming, because we can stick types into them, or objects that represent types, and so we can do manipulations that are based either completely or partially on compile time information. All right. So again, do stop me if you have any question. That's why. All right. Okay. So tuple, won't spend a lot of time on it, but so HANA provides its own tuple, just the same as std tuple, except it compiles much faster, but it's not strictly standards compliant. So it doesn't have exactly all the features that std tuple has, but it does so it compiles like 10, 20 times faster. If it's a trade-off you're willing to do that.
So what's missing?
The constructors, frankly, if you're just doing like pedestrian usage of std tuple, you will not notice it. But then you will also not notice the compile time difference probably. But what's missing is like no except is not like I don't bother with no except on the constructors. I do not have all the new what is it? I do not have all the new like movable if all the things are, what is it? Like there are some new fancy constructors in tuple that are just like completely too difficult to implement in a reasonable compile time fashion. So they're not there. So it's slightly more stripped down. But frankly, you would probably not notice that much.
It's about decomposition, like the state tuple. That's
What?
you can just decompose into fields using some construct. I forgot what it was.
Well,
With tuple, you can decompose without using the get number construct. You can just decompose like x, y, z equals something. I forget the construct.
so type.
Type,
Right,
yeah,
so
type.
no, HANA doesn't provide type, but that could be added quite easily. But frankly, it's mostly about the constructors. So not all exactly the same. I mean, I did that like maybe 1 year ago, so I don't quite remember exactly which constructor I did not add. But basically what I did was like take the standard specification of tuple, and then I said, okay, this cannot be implemented in a compile and reasonable way. Drop it, and so on and so forth. And I just I don't support allocators. Like if you use them, okay, too bad. But anyway, so don't want to spend more time on that. Now, if you want to index a tuple, you can do so not using std_get, but you can do so using your cherished operator bracket, because it's essentially like a vector, right? So why shouldn't we be able to just say bracket, give me the thing at this index? So you can. However, there's one twist to it. You have to pass in what we call what I will call for this talk, and I will call it in a very hand-wavy fashion, a compile time number. Essentially, it's a number that is known at compile time. But of course, if you just say 0, then the compiler knows that it's just the 0 literal, so technically it's known at compile time. But saying _c makes it really clear for the compiler that it's known at compile time. So essentially, under the hood, what happens is that _c is a user-defined literal which returns a stud integral constant. It returns an object which is not an integer, which contains the value 0, but saying like, hey, here's a value 0, and I know that like at compile time. And operator bracket is not taking like a size t or something like that. It takes a template type named t, and it takes a t. And depending on depending on whether it gets like integral constant of 0 or integral constant of 1 or of 2 or something, right? The different instantiation of the operator bracket will be instantiated. I'm mixing up my words, but anyway. So a different operator bracket will be instantiated, and so we will be able to know the index of compile time.
So those are in the HANA namespace?
The _c?
Yeah.
Yeah, you have to use HANA literals. Using namespace HANA literals. Then you get _c, and you also get _s.
Do you provide an unlimited number, or do you provide like 20, or like how high do the numbers go?
It's a user-defined literal. So basically, when you write this, there is a function called operator. It's operator quotes, double quotes, _c, which is and it's just a function that creates the thing. So I just provide the _c function. Well, user-defined literal, and you can create whatever you want with it. So there's no except if the compiler can't represent it, then you're kind of in a bad situation. But then that means that you have a big tuple, and you are in a bad situation, but for a different reason. So I won't go into much detail about this, but essentially that's a compile time number, and most things, whenever you need to pass an index or something like that in HANA, you're going to have to use a compile time index, so a compile time number. And the reason why that is because animals, depending on which index you pass it, it's going to have to return an object which is of a different type. So it really has to know like the index that you're trying to fetch has to know the compiler for the signature of the function to be resolvable. Yes.
So what happens at runtime? Do these objects go away, or do they?
What's that?
What happens if I want to use one of these things at runtime? What happens?
What do you mean, 0C?
Well, I guess I want to like look into, so I've got this animals tuple, it's a HANA tuple.
Yeah.
Can I use the animals tuple at runtime?
Oh, absolutely, yeah, I'm asserting on it. And here, Garfield could be input from the, like, okay, how many cats do you want? 3, all right. Well, no, that wouldn't work. Okay, you have 3 cats, name them. Give me the first name. I input this string from the student. Then, okay, here's the name of my first cat, and then you just, instead of adding Garfield, you would just have like the...
Okay, so you're mixing run and compile time there.
Exactly.
Okay.
Yeah. That's like, HANA is the fusion between, it should be called fusion, but there was already a language. so I was like,
Okay.
HANA, okay, all right, so that's it. So that's how you can index into a sequence. So my goal here, if you can tell, was really like to mimic as much as possible the usual interface that we have to access our data structures. My goal was not to have a insane syntax to do these things. And yeah, that's what it gives. Now you can insert stuff into a tuple. So if you have a tuple with a cat, a dog, and a fish, you can insert an elephant by just saying, hey, insert an elephant here at index 1 inside this tuple. And what it's going to do is going to create a new tuple which contains this cat, the new elephant that you just added, the dog, and the fish. It can possibly like insert it in place because we're changing the type of the thing, right?
Would auto more animals work? Would auto more animals work?
Would auto animals
More
work? Yes.
Okay.
Yes, absolutely, yes. The reason why I did it was to make it really clear that this is exactly what you get back. But yeah, auto would work. And then you can check indeed that the new thing that you just added is right. And by the way, regarding the question I just had before, the question was like, can you use